Hello and welcome back. The purpose of this video is going to be to apply the first law of thermodynamics to a problem from your openstax textbook. So thermodynamics' first law is the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. And recall that internal energy from chapter 13 can be written in two different ways. You can either write it as 3/2 nRT, where n is the number of moles and r is the gas constant, or you can write it as 3/2 capital N KT, where capital N is the number of molecules and K is Boltzmann's constant. So we can use either form for internal energy. The problem that we're going to look at in this video is 15-10 from your openstax textbook, and it reads as the following. A car tire contains 0.0338 cubic meters of air at a pressure of 2.20 times 10 to the 5th newtons per meter squared. How much more internal energy does this gas have than that same volume has at 0 gauge pressure, which is equivalent to normal atmospheric pressure, 1.013 times 10 to the 5th newtons per meter squared. So we want to find the difference in internal energy. So you can see that, and we're told that the volume remains constant. So the volume, 0.038 cubic meters, is V1 and it's also V2. The pressure P1 is 2.20 times 10 to the 5th newtons per meter squared, and the pressure P2, 1.013 times 10 to the 5th newtons per meter squared. We want to find the difference in internal energy, and also N1 is equal to N2. In other words, they're the same number of moles, and we're going to say that the temperatures are also, the temperatures are not also the same. We want to find the difference in the temperatures, or the difference in the internal energy. All right, so taking these equations, we can find that U1 can be written as 3/2 N1R T1, and U2 can be written as 3/2 N2R T2. So we need to be able to re-express these temperatures because we don't know them. So we want to go back and use the ideal gas law to re-express them. Remember, P times V is equal to nRT, so I can solve for T as PV over nR. So now let's substitute those into U1 and U2. So U1 is going to be equal to 3/2 N1R, and then T1 is going to be P1 V1 over N1R. And you can see your N1 and R's cancel. And then U2 is going to be equal to 3/2 N2R. Substituting T2 in, we're going to have a P2 V2 over N2R, and the N2s and the R's cancel. And so now, forming our subtraction here, U1 minus U2, we're going to have 3/2 P1 V1 minus 3/2 P2 V2. There's a lot of commonality here. Remember, V1 and V2 are the same, so V1 equals V2 equals just V. So we can factor that out. So U1 minus U2 can be written as 3/2, which is common to both of them, V, which is common to both of them, times the difference in pressure, P1 minus P2. So U1 minus U2, plugging in some values now, 3/2 times the volume, 0.038 cubic meters, that's the standard unit, times the difference in pressures, and so this is 2.20 times 10 to the 5th newtons per meter squared, minus 1.013 times 10 to the 5th newtons per meter squared. And when you plug those into your calculator, you get a difference in the internal energy of 6,772. 6,772, and the units are going to be Newton meters, right? Because meters in the denominator squared will cancel all but 1 meter in the numerator of the volume, and so then we'll have a Newton times a meter, which is a joule. And so we'll express that as 6 point, let's see, we're on 2 figs here, 6.8 times 10 to the third joules. So there's a difference in internal energy of 6,800 joules when we change the pressure from 1.013 times 10 to the fifth newtons per meter squared to a pressure of 2.20 times 10 to the fifth newtons per meter squared. So this gives you an idea of how to apply it to one of the problems from the textbook. In the next video, we'll work actually a PV diagram problem so you can see how those problems are looked at, and then you can apply those in class as well. So we will see you then.